Welcome back to 6th grade science. Earlier this week, we continued our discussion about electricity, and today we are going to be bringing that discussion of electricity to an official close. Remember, just because we are officially closing our discussion on one topic doesn't mean we're necessarily done with it, because science builds on one another. We're going to start today talking about electric power. This is the rate at which a device changes electric current into another form of energy. The SI unit for electrical power and power in general is the watt, W-A-T-T. When we talked about energy way back when, we talked about joules, and we talked about work, and we talked about joules with work. 1 watt is equal to 1 joule of energy per second. With high voltage, you often hear it referred to in the form of kilowatts. Kilo is 1,000, and since it's in front of the word watts, it means 1,000 watts. So 1 kilowatt is equal to 1,000 watts. The total amount of power measured in watts is equal to current measured in amps times voltage. Just like with Ohm's law and the formula associated with that, you can use the power formula here to figure out different calculations. So if you know the current and the voltage, then you can figure out the power. If you know the current and the power, then you can figure out the voltage. And if you know the voltage and the power, you can figure out current. So now we know that electrical power is using a device to change electrical energy to some other type of energy. What can electrical energy be used for? Well, this depends on the power of the appliance and how long the appliance is used. To figure out the total electric energy, we're going to have another formula. So the last one we talked about was power. This one is going to be electrical energy equals power times time. So it's the amount of power over the elapsed amount of time. With this equation, we can calculate different things just like Ohm's law and the power equation that we talked about. If we know the amount of power and the length of time, then we can figure out the amount of electrical energy used. If we know the amount of electrical energy used and the amount of power, then we can figure out how long it was used for. If we know how long it was used for and we know the electrical energy used, then we can figure out the total amount of power used. So if you have noticed with these descriptions of the different formulas, I keep talking about the different way that these formulas can be used to calculate different things. The reason being, you have the base formula, and it can be rearranged on figuring out, okay, I want to know this component. The formula can be rearranged because as long as it's rearranged properly, with multiplication, division, switching sides, then it can be used to calculate the different components. I'm not really going to go super in depth on how to do that. That's something that you'll go over in math classes as you continue on in your educational career. But for right now, it's just important to note that you have one formula and you can use it to figure out a few different things depending on what you already know. Since we're talking about electricity as a whole, what it is, we're getting into real-life applications with series circuits and parallel circuits and the different use of electrical energy. It's also important to talk about electrical safety. Electricity is very dangerous. Contact with it can start a fire, it can cause injury to yourself, or even death. So when working with anything electric-wise, it's very important that you take safety seriously. One issue that can lead to fires is a short circuit. Short circuits occur when the electric current takes a path that is shorter than the original intended version. Here I have an electric cord. It's part of my computer cord. And it's hard to see on this one, but before there were times where the cord would have a split down the middle, and you could see that there was 2 different wires in here. There is a wire that goes from the power source and takes the electric current to whatever item you're trying to charge, in this case my computer. And then there's another wire that brings the electricity or the current back from my computer back to the outlet. So it's that flow of electrons from point A to point B. In the case of a short circuit, one of these wires could become damaged and then interfere with the other wire. So what happens then, especially if it's a break in the wire, the electrical current would come in and then it would go to that break and then come back rather than completing, because it might not be connected to the wire up here. So if it's not connected, then the electrical current can't go through it. Or it could just be that more of the wire is touching the other side. And remember, electricity is going to go the path of least resistance. So if you have a little bit of wire going up, a little electricity will go through it, but not much, because more of it will go to the side where the larger wire is. In this case, the break. What happens when the electrical current takes the shorter path is it produces more heat. And eventually this heat can in turn overheat, and then when this occurs, it can start a fire. As electronics have continued to develop, more and more safety features are being built into our different electrical components. Back in the day, a lot of electrical devices had two-prong outlets, like my computer charger does. Nowadays, it's much more common to see the three-prong plug, and that's because this is an added safety feature. Circuit breakers are also a good safety feature. How a circuit breaker works is that it controls different areas of whatever building you're in. And each of those areas have different parts that are attached to that circuit breaker. So if there's an electrical issue anywhere along that particular area, the circuit breaker trips. And what this means is it shuts down electricity to that area. If there was an issue with a short circuit somewhere, that circuit breaker can trip, turning off the electricity. No electricity means that area won't overheat and is much less likely to cause a fire. Another modern safety feature is GFCI outlet. This stands for ground fault circuit interrupters. And what these do is similar to the circuit breaker. When a ground fault occurs, they shut power off to that area, specifically that outlet. Aside from modern safety features, there are things that you can do when using electricity for your safety and the safety of those around you and your home. For starters, never mix electricity and water. I mentioned it in the last video, but to reiterate, most water contains impurities, which allow it to be a good electric conductor. If it was pure water, it wouldn't conduct electricity at all, but more often than not, you're not going to come across that in real life. Instead, it's going to be water with some type of impurity in it, which means it is a good electric conductor, so you should not mix electricity and water. For this, don't plug in any appliances into an outlet when your hands are wet, when you're standing in water, or when you're in the shower or bathtub. The reason you shouldn't do this is because if your hands are wet and you come into contact with the prong or an electric spark as you're plugging it in, the electricity can travel through the water to you and then injure you. Next topic is overloading a circuit. Try and avoid overloading a circuit. And how you do this is try and avoid plugging in too many devices to one outlet or into extension cords. So if you have an extension cord plugged in with a power strip and another power strip plugged in, what you're doing is increasing the amount of current that's traveling to that area. When you increase current too much, it can overheat and then in turn cause a fire. If you notice that a device has a damaged cord, never use that device. When I talked about short circuits, I talked about having one part of the cord broken and that causing a short circuit. The short circuit example typically leads to fire, but it can also lead to sparks or shocks. So if you plug a damaged cord into the wall and then accidentally touch an area of exposed wire, you can get shocked. You should never plug anything into an electric outlet that's not designed to fit into the plug. So computer cable, it's fine to plug in because you have the plug. A knife or a fork or a coin that I find, or even a silly piece of wood. You should never put anything that's not a plug into an electric outlet. This can cause a shock, especially if you're holding the other end. The electric current can travel through the item into you. For the last little bit of safety tips, never go near fallen electric lines. We've talked about it before, but remember they carry an electric current with a very high voltage, and this is extremely dangerous to be around. If you come across any fallen power lines, make sure you call and report it and don't try and do anything yourself related to it. All right, stepping away from the safety aspect, we're now going to talk about electric signal. What is an electric signal? It's a message that's encoded using an electric current. Any device that uses an electric current for this is known as electronics. So your computers, your phones, your iPads, the camera that I'm recording this on. In order for them to encode messages, the voltage has to change rapidly. and over again. There are two different ways for these changes to occur, which leads to two different types of signals. You have analog signals and digital signals. Analog signals consist of continuously changing voltage in an electric current. This was actually the first type of electric signal to be invented. So if that tells you anything, it's a little antiquated at this point. One of the reasons that it's not used very much anymore is that it's very susceptible to distortion and noise. What you see analog signals in nowadays is more so microphones, or some mobile phones still use them as well. Much more modern is digital signals. Most modern day electronics use digital signals instead. These consist of rapid pulses of voltage that continuously turn the electric current on and off. This encodes data in a string of zeros and ones. The zeros are when the current is off, and the ones are when current is on. And this is known as binary code. When these were discovered, they ended up taking over the place of analog signals in most things because it's easier to transmit and it's more reliable than the analog signal. It's also much more accurate. Now, I mentioned that electric signals are used by electric devices, and I've talked about electric devices using power. I've talked about electric devices a little bit in general. What are electronic or electric devices? In order to talk about what electronic devices are, I have to talk about what's in them, and these are electronic components. Electronic components consist of semiconductors, which mainly consist of silicon. Now, these are called semiconductors because they conduct electricity better than insulators, but not as good as conductors, so they're in between, hence semiconductors. How they create these is through something called doping. They have a crystal with a bunch of silicon atoms in it. And then what they do is they remove some of the silicon atoms and then replace them with something else. Depending on what they're replaced with, it gives them more or less valence electrons than silicon. This is what allows a semiconductor to conduct an electric current. There are two types of semiconductor. You have your N-type and your P-type. The N-type, otherwise known as a negative semiconductor, consists of silicon and atoms that give extra electrons, making it negative, which is why it's called an N-type or negative type. One common example of an atom that's used is phosphorus. This is like the negative terminal of a battery. P-type, or positive type, on the other hand, are different. These consist of silicon and other atoms that have positively charged holes where electrons are missing. Because they are down electrons, they are positive. One common example is boron. Just like N-type is like the negative terminal of a battery, P-type is like the positive terminal of a battery. Semiconductors are the most basic electronic component. From there, you combine them to make different things, like a diode. A diode is an electronic component made with two semiconductors. Diodes are used to change an alternating current, which remember is point A to point B, back to point A, back to point B, to a direct current. So from point A to point B, point A to point B. The next thing you have is a transistor. Diodes are made with two semiconductors. Transistors are made with three semiconductors. This is used to either turn on or off current or to increase the current overall. Last but not least, you have integrated chips. You know what these are, or you've heard of them, because another name for it is the microchip. These are electronic components that consist of many other electronic components. More specifically, they consist of diodes and transistors. These microchips are used in modern day electronics to carry out specific tasks. So depending on what task you have, you'll have a different microchip. So we've talked about the different parts. What's an electronic device? Simply put, electronic devices are those that use an electric current to encode, analyze, or transmit information. Specific examples are ones that you're probably very familiar with. These are your computers, your cell phones, your iPad. Like I said earlier, the camera that I'm using to make this video. If you've ever seen the inside of a computer, you know that the components are very small. Computers themselves are made up of millions of electronic components. That brings us to a close of our discussion with electricity. Like I said before, just because we're officially done talking about it now doesn't mean we're actually done talking about it. Next up, we're going to be working on magnetism. As always, if you have any questions, please don't hesitate to reach out to your teacher, whether that's Ms. Cameron or myself. Bye!